right now, I am going to introduce our keynote to begin this by the name of Jeff Dean. I think most people know Jeff, so I don't know if I should really introduce him. But he's a Google Senior Fellow. He leads up most of the machine learning and infrastructure that powers all of the systems at Google. I'm really excited to have him here to talk to you about all his work and also the applications that it lends itself to. So as the entrepreneurs in this room are thinking about what to do, what are the next startups, I think it'll give you a lot of ideas as well as to where this exciting technology is headed and how you can plug yourself in. So with that, I'll welcome Jeff.
Thank you. What I'm going to talk to you today about is some of the work we've been doing the last 4 or 5 years about trying to make really intelligent computer systems using machine learning. And I'd like to point out this is joint work with many, many, many people at Google. We have a lot of people working on this both in our team that does machine learning research, but also in lots of different product teams using kind of the work that we've done to deploy that in real actual products. And I'll cover some of that today. Obviously, one of our goals is we like to build intelligent products so that we can save people time, so that computer systems can really understand, the kinds of information they're seeing and actually provide help to people. And that kind of intelligent product is actually really hard if the computer system can't actually understand things. So what do I mean by understanding? So if you as a human saw an image like that, you would have no problem generating a sentence or a caption for this image saying, it's a cute little girl, she's hugging a teddy bear, things like that. But computers have traditionally been not that great at taking inputs like that, taking a bunch of pixels and really understanding what they're observing. And by understanding what they're observing, we'll be able to build much more interesting and better products. You as a person know that you'd go to that yellow awning place to get the lowest prices, of course, and that the other place sells gifts. But computers traditionally have not, we've had street view cars driving around the world taking pictures of street scenes, but mostly we've just been showing those images to users when they want to see what a particular block in the world looks like. But we'd like to be able to extract information that a human would be able to discern by looking at such an image. Similarly, when someone speaks, you have no problem understanding me, at least I hope not. We'd like computers to be able to understand spoken language as well as humans do. When you're having a conversation, it's very fluid and easy because people understand what you're saying quite naturally. And we'd like computers to have that same fluidity that people do. Okay, so what is machine learning? So there are two heavily overlapping fields. There's the field of artificial intelligence, which is the study of how can we make intelligent machines intelligent. And then there's the field of machine learning, which is how can we make machines that learn. And this overlapping area in the middle is, I think, a very interesting area because it's essentially the part where we're making machines that learn to be intelligent. And that often turns out to be actually easier than telling a machine how to be intelligent. Instead, if you have a machine and you train it to learn from observations of the world, of data, of images, of text, and it can learn the kinds of patterns that occur in the world, that's actually a much more powerful mechanism for making intelligent systems than trying to sort of encode all information in the world in explicit instructions. So this is an illustration of this. If you were trying to tell a computer what spam is, email spam, you'd have a long list of rules, and those rules would have weights or something, and it would be very long and complicated, and it would be very brittle. And instead, if you have a training set of these emails are spam and these ones are not, and you train the system to say, I'm going to try to predict on an email whether it's spam or not, and then change itself to reduce the errors, learning from all the examples you're now showing it, that's actually going to be more powerful because as you collect more examples, the system can use those and adapt its understanding of what is spam and what is not using the new data that it can observe. So most of what I'm going to talk about today is a particular kind of machine learning, which are called neural networks. So neural networks essentially can learn very complicated functions from data, and I'll give you examples of functions that they can learn. here they transform one space into another space. And the kinds of things they can do are where one of the spaces might be the pixel values of an image, the red, green, and blue values of a photograph you've taken. And space 2 might be the probability that that photo contains a cheetah. Right? So this is a very complicated function. It's going directly from a whole bunch of pixel values to something very high level and understandable about that input. They're actually quite powerful models. One of the things that makes them powerful is, as you see here, the inputs are pixels and the output is, I think that's a cat. They build on each other using these simple trainable mathematical units. So typically they're layered in this way where the layers that are close to the input learn very primitive kinds of features. They learn to predict, does this little bit of the image contain an edge, this orientation, or is it mostly green, things like that. And then the later layers build on top of those earlier, more primitive features. So they learn, oh, there's a corner here, or there's something that looks a little bit like an eye, and so on. And this kind of layered approach allows you to create more and more powerful abstractions automatically through learning, basically through observing interesting input and output examples of the function you're trying to approximate. So this is loosely based on what we know about how real brains work, in the sense that we have neurons in this model that are simulated that behave somewhat like real neurons in real nervous systems. They take in some inputs, they weight those inputs, some inputs are more important than others, and then they emit a response. But that's the level of fidelity of things here. We're not simulating brains at the level of kind of the neurotransmitter level or chemical reactions that are happening, but at a very high level abstract notion of what a neuron is. Just to give you an example, so that might be a neuron, that thing on the right, that takes input from this little 5 by 5 patch of neurons below it. And each one of those 5 by 5, so there's 25 inputs to this neuron, and each one of those will have a weight associated with it. And what we're going to do when we're learning is make little adjustments to those weights to try to get the model to do a better job of what we think it should do. Basically, given the data we're giving it, to do a better approximation of saying that image is a cat if I see the pixels that I showed you before. So it's a relatively simple mathematical function that each neuron implements. The W vector there is the weights, so 25 floating point numbers. The X there is the inputs. Those are also numbers. So we're just doing a weighted sum of those things. We add a little thing to bias the neuron. And that's a very simple mathematical function, but a real model that's composed of 1 million or 1 billion of these little simple mathematical functions that is all collectively trained to accomplish a task is a very, very powerful thing. What this looks like in pictorial form is, it's a PDF, so I will skip that. That was an animation. You can actually see how this works yourself in a little thing that our group has put together called playground.tensorflow.org. This allows you to simulate very small numbers of neurons. So this is a 4-neuron layer followed by a 2-neuron layer. And it's kind of an interactive thing. It's kind of fun to play with. And you can choose different data sets and see how well the system is able to predict the output from those data sets. It gives you real intuition. But this is really a very toy-sized thing. This has 6 neurons in it. And real models will have millions or tens of millions of neurons in it. But it's good for building intuition. OK, so one of the really important properties of neural nets is that the results tend to get better when you have more training data and you have a bigger model to capture the more subtle patterns that are present in that larger training set. And obviously, the first 2 of those imply that you often need more computation in order to do this learning process. The learning process involves going over the training data many times, making little adjustments to all the weights and all the neurons, and hoping that through learning, through training, you're going to do a better job approximating the data that you're observing. And also better algorithms and new insights into the kinds of model structures that work well is another important thing. So one thing I want you to take away from this talk is that neural nets in particular are surprisingly general. You can see all the different areas that we've applied neural networks for to solve different kinds of problems. And some of these are perceptual problems that deal with image pixels and imagery data. Some of these are speech data that deal with kind of signal processing of speech audio signals. Some of these are natural language things that deal with streams of text. And the same underlying algorithms and rough model structures often can be applied to all these different areas. So this is why the field of machine learning is really important and exciting, and in particular neural networks, because they're so applicable to so many different areas. And as a reflection of that, we've been building software that other groups at Google can use to train neural networks for their particular problems. And there's a lot of different groups, different products at Google, a lot of different kinds of sub-teams within those products. And what you see is this exponential increase in the number of different teams, effectively. This is sort of a proxy for that. The number of different directories in our source code base that have neural net configuration files for our training software. That's a good approximation of like how many different teams and people across Google are experimenting and using this. And if you look at the directory names, it's across many, many different product scenarios. Again, a sign of how applicable these models are to different kinds of problems. Okay, so let me go through some of the examples of models that we've been able to train, and then how we apply those in different Google products. So one of the first things that we did was work with our speech recognition team to deploy neural networks as a key component in the speech recognition system. So essentially, you're trying to go from audio to a transcript of what that person actually said. Goes from that acoustic input, which has frequencies and time, and how cold is it outside is the output you want. And by using neural nets, we're actually able to train a much better speech recognition system and reduce the errors by more than 30%. And the system works better in kind of noisy environments or crowded rooms or with different accents. And that actually dramatically improves the usability of the system. Another area where we work with product teams to deploy neural nets is in photo search. So essentially, Google Photos allows you to upload your photos and then manage them and share them with people. But one of the nice features it has is the ability to search your photos based on what's in them without you having to type them at all. And it's able to do that because we have a neural net that can map from the raw pixels of an image, something like that on the left, even though that's not a great photograph, it's kind of whitened and has a little overexposure, we can still say that photo is a picture of an ocean. And that allows you as a user to take all the photos you've taken and search them based on what's in them. And so we can cluster things so that we can automatically make little sub-albums of all the kind of categories of things you might have in your photo album, and you can search my photos of Siamese cats, and you actually get mostly Siamese cats, certainly all cats. It's Google, so we like cats. Here's something a public user posted publicly. He's like, wow, the new Google photo search is a bit insane. I didn't tag those. So he's able to find all his pictures of statues without actually, and we can find Yoda, despite that being an unusual looking Yoda. It's always nice when you can retrieve the macrame Yoda. And the possibilities of using computer vision for lots of different tasks are basically in front of us today. So there's lots of different ways, once a computer can actually understand what it's looking at, to use it in kind of new and interesting ways. Here's just one example. A small group of people at Google realized that neural nets could be used to solve this particular problem, which is to find roof areas in Google Maps, and then do some analysis of those to tell you as a homeowner how many kilowatt hours solar panels installed on your roof could actually generate, based on understanding what the slope of the roof is from the shadows that the satellite imagery shows across different satellite views of your home, and how big the roof is. And then it's sort of a very convenient way. Typically, you'd have to have a solar installation person come out and gaze at your roof and estimate this, but we can do this automatically. the recent success of our DeepMind group in London in playing the board game of Go, which has been one of the last holdouts for human board games in terms of being much more difficult than chess. We recently defeated the world champion Lee Sedol in Korea in March. And one of the key components of that was essentially a neural net that could observe any Go board configuration, and for all the empty squares where you might move, predict the probability of where, if you go here, your probability of winning is 83%. And if you go here, your probability of winning is 4%. And so it allows you to get kind of that human intuition when you're an expert Go player of just glancing at the board position and saying, oh, these are the 3 or 4 places on the board I should really think about going, and I shouldn't think about going anywhere else, because those ones are not going to be good moves. And that's a really key component, because the game of Go has so many possible spaces to explore, you can't possibly simulate all the different paths of where you might move and where your opponent might move. Another thing that we have done is launched a feature called Smart Reply. It was actually Google's April Fool's joke in 2009. We said, haha, we're going to produce this software that will reply to your emails for you. But then we actually decided we would do it. And so we launched this last November. And essentially what this does is it takes an incoming email in your inbox and using a language model tries to predict what are short responses that you as a human might generate for that email. So to give you an example, here's one that my teammate received from his brother saying, hey, we wanted to invite you all to join us for an early Thanksgiving. Please bring your favorite dish, RSVP by next week. So the first thing we do is we run a small neural net that says, do we think a short response would make sense to this message? If yes, then we activate a much more complicated model that actually takes in that message a word at a time and tries to understand the context and what kinds of replies would make sense in that context. And so you see here, the 3 responses that the system generated were, count us in, we'll be there, or sorry, we won't be able to make it. And this is useful enough that it's actually very hard to type responses on a mobile phone. That's sort of one of the main sort of reasons that, sometimes I defer responding to an email until I get to a keyboard, because it's just kind of a pain to type. But this actually allows people to very quickly on the fly respond to emails with the kind of the appropriate response. And 10% of all email replies in the inbox application are now generated with this feature. So this is something that really just, because we can understand text and understand context, we can make features that users really love and will make them more productive. Another example is this video, which will not play because it's a PDF. I will skip it. OK, so back to understanding that photo of the little girl. Our group has actually done research to take a model where we take pixels as input, so we take pixels from the image there, and we actually can generate human sentences in English that describe that image. And the training data we used was other images and sentences that humans had written. And so this is an example of a test image that the model was never trained on. And it's a generative model, so it can actually generate multiple plausible sentences from that image. And in comparison, the test image, a human generated a young girl asleep on the sofa cuddling a stuffed bear, but the model generated these 2 sentences, a close-up of a child holding a stuffed animal, or a baby is asleep next to a teddy bear, which are pretty good. If you'd asked me 5 years ago, could a computer do that soon, I would have said, I don't think so. But this is a sign of the progress, especially in the area of computer vision and language modeling, that I think computers can now actually do that. And that's pretty transformative. Here's some other examples. You'll notice they kind of lack the subtlety that a human might put on this. Like that first image, they might say, a tennis player about ready to serve the ball, because the human might understand a little bit more about that context. We kind of say, yes, it is a man holding a tennis racket on a tennis court, but that's perhaps less subtle. That's actually 3 pizzas, not 2 pizzas. They're just on 2 pans. When it messes up, it's sort of funny, but you can sort of understand why it almost said that. I assure you, if you squint just right, there is a man flying through the air riding a snowboard. Okay, so let me switch gears a bit and talk about the underlying software that we use to train a lot of these systems. So when you're building machine learning systems like the ones I just described, you want a lot of different kinds of things. You'd like to be able to easily express different kinds of machine learning models so you can try out lots of crazy ideas. You'd like the system to be scalable so you can run experiments quickly on large data sets. It'd be nice if it was portable so you could take the same model and train it on a data center, train it on a desktop computer, and then maybe run the models on a desktop or run the models on a phone. Reproducibility is nice, so if you and all your friends use the same system, you can share results and share models more easily than if you're each using different kind of underlying software. And you'd like the ability, once you have something that works well, to not have to re-implement it to put it into production in a real system, but to be able to have the system sort of flexibly go from a more research exploratory environment to something that you can actually deploy in a real product. And so this is the software that we came up with. Our group has been working on this system. This is kind of our second generation system for training neural nets. The first generation we learned a lot from, and this system is kind of fixes some of the problems we saw with the first system. So TensorFlow is essentially an open standard software for doing general purpose machine learning. It's really good for deep learning, the training the kinds of neural networks that I described, because that's a lot of what our group focuses on, but you can do all kinds of other kinds of machine learning in it. We released this system as an open source project in November after working on it for about a year internally. And it's licensed under a very flexible Apache 2.0 license. That license basically says you can do pretty much whatever you want with it. It's been pretty well adopted. So TensorFlow, this is a measure of kind of adoption on GitHub where the source code is hosted. People can star repositories that they're interested in, or they can fork them when they're actually using them. And TensorFlow was released last November, so it's been out for about 6 months. These are some other open source projects for doing neural network training. And you can see the TensorFlow is already sort of more popular by a significant margin than many of these. People seem to really like the combination of sort of flexibility and production readiness that TensorFlow provides. And the motivation for building this system was our first system was actually quite good on the production readiness, but not quite so good on the sort of research flexibility standpoint. If you wanted to do things that fit well within it, it was easy. If you wanted to do something a little different, it was sometimes quite hard. And so basically just by using the first system, we got a better understanding of the kinds of things we should really be building. There's the website. One of the things that I think has made it reasonably popular is we put together a bunch of tutorials that show how to use the system for a bunch of different kinds of problems. In particular, some of the ones that I described here, like computer vision models or language translation models. These all have nicely written tutorials that both describe how to do it in TensorFlow, but also how the model actually works. Okay, so some of you may be wondering, how can you get started in machine learning? And I think there's a variety of different ways. One is a lot of cloud services are now offering kind of pre-trained APIs that I'll talk about in a minute, where you don't have to even really have much understanding of machine learning. You can just kind of give us an image, and we'll give you back good stuff from the image, good information about that image. And going down are sort of more and more complex ways that are more flexible, but require more understanding of machine learning. And I'll talk about all of them. So these cloud-based APIs, these are Google's cloud-based APIs. Other cloud providers are also starting to offer these. We think ours are better, but you should check them all out. And these are things that allow you to, for example, translate from one language to another, or do speech recognition or vision. I'll show you some examples of the vision one. So you can just upload an image like that, and we'll tell you, we think that's a running scene and maybe a marathon. And on the right, you can upload that image, and we'll tell you, here's where the faces are in the image. We think this face, that person is happy. Here's some text that we found in the image, and we think it's in Spanish, and the actual ASCII characters are abierto. So, without any real machine learning understanding, you can just give us pixels and we'll give you back information like that. And you can build really intelligent products around that. using these kinds of pre-trained models. You can also essentially take that same model and download it and run it on your own computer. It's a little more work. You now have to set up TensorFlow and run it on a computer as opposed to just talking to our cloud APIs, but that allows you to do the same thing, and we'll tell you, that's a panda bear. You can actually train a model starting with one of the models we've trained, and then do a bit of additional training on maybe a data set you really care about. So maybe you have a data set of flowers, and you want to identify very specific kinds of flowers. You can start with that and then train a model on your flower data and get a model that is good at detecting which kind of species of flower something is. And then finally, you can use TensorFlow in kind of its rawest form where you can develop your own machine learning models. Okay, so what does the future hold? I think you saw that exponential graph of internal usage at Google. I think this is going to continue both within Google, but also externally as other companies and organizations adopt machine learning and start to realize, pixels are not this thing that computers can't understand. They're things that you can actually use machine learning and extract real information from them. I think it's going to have a big impact in fields like robotics, self-driving cars, healthcare, video understanding, dialogue systems, lots of things. So just to give you a taste of that. Right, so this is a system that we're essentially teaching robots how to grasp objects based on camera inputs. So this model, it's a neural net. It goes directly from cameras mounted above the robotic arm directly to torque motor controls for the different motors in the robot. And these robots just have bins of stuff in front of them, and they try to pick stuff up all day. And if they succeed, that's a supervised problem, because if they succeed, then the gripper doesn't close all the way. If they fail, the gripper closes all the way, and then they can't pick it. They've failed to pick it up. And so we can use that data to essentially bootstrap better and better grasping models for what kinds of grasps work well on different kinds of objects. And these are some of the grasps that the model kind of learned to do, and it can grasp things at different orientations. So it's essentially learning hand-eye coordination, and we have 20 of these robotic arms set up in a lab, and over a period of several weeks, they've gone from really terrible grasping to actually pretty good grasping. So that was the thing I wanted to show you, and go back to here. They're making significant strides in lots of different areas I've described, and there's some further reading. So thank you.